I confess it's some time since I read Alice Through the Looking Glass before preparing for these lectures, and I'd certainly forgotten the words of the nonsense rhyme about the Jabberwock. So, to begin with, I'm going to ask Alice herself, in the form of Louise, if she will bring us up to date and read us the first two verses of the nonsense rhyme.
'Twas brillig, and the slithy tove stood gyre and gimble in the wabe. All mimsy were the borogoves, and the mome raths outgrabe. Beware the Jabberwock, my son, the jaws that bite, the claws that catch. Beware the Jub bird, and shun the frumious bandersnatch.
Thank you, Alice. Gyre and gimble in the wave. Gyre and gimble are the words that invite us to study gyroscopes in gimbal rings. Gyroscopes like this beautiful Victorian gyro, all with its own weights and contraptions. I'm going to spin it and immediately ask a volunteer to come and give it a push. So first of all, I'll spin. Now, someone come and just put your finger on this little button here and push towards me very gently. Again, keep pushing. Thank you. It didn't yield to her push, you see. It will go either way. It did something different. Now, we call that something different precession, and I shall have a lot more to say about precession in a few minutes. The Jabberwock was a monster with many heads. It was as if it was, for me, a representative of the way we divide our science into physics, chemistry, biology, and then we take one of those, like physics, and we divide it into heat, light, sound, electricity, and magnetism. Then we subdivide that, and so on. Now, some of these heads of the Jabberwock are really laws of physics, I suppose, for me. And some of them look into mirrors and see their own reflections. And they then think there are more of their kind than there really are. The same can probably, from an engineering point of view, be said about the so-called fundamental particles. They try to coexist with each other. Now, the idea of science, in rather perhaps the profession of science, as a monster, is not a new one. Martin Gardner, my favourite author, put it in a neat way in a chapter on the fall of parity. And we talked about parity last time and said that parity was to do with the universe as a whole being handed, having a preference for left or right-handedness without saying which. And Martin Gardner wrote this: "Not one of the three experiments that first toppled parity would have been performed at the time it was performed if Li and Yang had not told the experimentalists what to do. Li had no experience whatever in a laboratory. Yang had worked very briefly in a lab at the University of Chicago, where he was once a kind of assistant to the great Italian physicist Enrico Fermi. He had not been happy in experimental work. His associates had even made up a short rhyme about him, which Bernstein reports. Where there's a bang, there's Yang. Laboratory bangs," went on Martin Gardner, "can range all the way from an exploding test tube, or in our case, a Mr. Coates special, to the explosion of a hydrogen bomb. But the really big bangs," went on Martin Gardner, are the bangs that occur in the heads of theoretical physicists when they try to put together the pieces handed to them by experimental physicists. One of the things that you may not have been made sufficiently aware of is that there is apparently no simple connection between gravitational mass and inertial mass. When you compare two masses, you can do it either by weighing each on the same spring balance or by subjecting each to a known force and measuring its acceleration. And the two methods always agree in the answers absolutely. And so, although there's no simple connection, these two heads of the monster must in some way be a curious kind of reflection, the one from the other. Now, in the Jabberwock nonsense rhyme, Lewis Carroll invented some lovely new words, especially for me, slithy and mimsy. They were explained later as combinations of other words which allowed him to express two ideas at once. Lithe and slimy gave rise to slithy. Miserable and flimsy gave rise to mimsy. Now, engineers have been employing this word combination idea for some time, and at first I must say that the words were scorned by the pure scientists because they didn't describe anything that was quantifiable. You couldn't measure it, so it didn't exist. That is a philosophy of its own. But one of the useful ones, which has now become respectable, I will demonstrate to you with the help of 4 blocks of metal on a nicely polished plane surface, and I am going to tilt the plane and see whether all the blocks slide off together as the good book of applied mechanics tells us they should. When the angle of the plane, oh dear, there's one gone already. When the angle of the plane reaches the angle of friction, they should all slide together, but I'm afraid they don't. And if you want to repeat this experiment, you'll have to polish the plane very carefully and clean the blocks. Now, the angle of friction determines the coefficient of friction. Last lecture, I promised you jam tomorrow. Jam you shall have. And tomorrow you shall say we had jam yesterday. Strawberry jam. Now we will do an experiment in friction. I can see myself getting into trouble with some of your mums when you get home and start doing this. Now let us see what the good mechanics book has to say about the laws of friction. That's gone. The friction was increased. Mu had a bigger value. Mu for that one has a very large value. Mu equals, nearly, the lot, nearly infinity. The angle of friction is now 90, and mu is infinity. We can handle infinity, but what about more than infinity? Now you know what's going to happen. After a while, they're going to peel themselves slowly off the goo and drop. And you see that you made the difficulty for yourselves by defining a coefficient of friction such that if they stuck on the vertical, the coefficient of friction was infinity. A lot of rubbish. The engineer knows what he's doing. He knows what's going on. And it is the job of the engineer to interpret science. You mustn't let it get too pure that it becomes a nonsense. And as far as I'm concerned, I go along with Humpty Dumpty. When I use a word, said Humpty Dumpty, it means just what I choose it to mean, neither more nor less. And so say I with emphasis. For after what I thought to be a clear exposition of a subject in this theatre last November, my use of the conservation of momentum principle was interpreted as a claim to have created momentum out of nothing. How anyone with a PhD could get that wrong, I cannot imagine. But when the journalistic editor got at it, the headline was something like, "Newton was wrong, says Professor." Professor said nothing of the kind. But from then it's a short step to perpetual motion, energy creation from nowhere, and half the crackpots in the kingdom are writing to me, solving the world's energy crisis. It's like the whispering game at a party. After that follows the slings and arrows. You have no idea. And talking of crackpots, Freeman Dyson made these comments in an article in the Scientific American. Most of the crackpot papers which are submitted to the physical review are rejected not because it is impossible to understand them, but because it is possible. Those which are impossible to understand are usually published. In the same article, he wrote of a lecture in New York by Pauli to a group of scientists that included no less a person than Niels Bohr. In the discussion that followed the talk, younger scientists were sharply critical of Pauli. Bohr rose to speak. "We are all agreed," he said to Pauli, "that your theory is crazy. The question which divides us is whether it is crazy enough to have a chance of being correct." Now, circularity is a powerful concept. In circular motion, there is magic, as there is in that other thing we call electromagnetism. But like that subject, the magic is not apparent until it is like, shall we say, rather than its reflection, it's like its neighbouring head, truly three-dimensional. A coil of wire in 1830 was said to have a property all its own, which was called resistance. This was a property of this coil. You could measure it by measuring the ratio of the voltage across it to the current flowing in it. So I will pass some DC into the coil. Sorry? I beg your pardon. Yes, you go. Pass AC into this coil. We've got about 5 amps of it, have we? No, less than that. We want some more. That's it. About 5 amps of that, yeah. And then we can use a second coil merely connected to a voltmeter. When I put this second coil on the top, it gets some induced voltage by a mechanism which I do not understand, and I suspect neither does anyone else. But if I turn this second coil at right angles, it's always been our experience, you can find a place where the voltage is zero, as long as the coils remain at right angles. It's as if they lived in separate worlds and didn't want to know about each other. Now, in that respect, I was reminded by a drawing by M.C. Escher, who's done many marvellous drawings, that it was like the drawing of the men on the staircase. And of them, the artist himself said, "Here we have 3 forces of gravity working perpendicular to one another. Here is an artist being more of a scientist than we are ourselves. 3 earth planes," he said, "cut across each other at right angles, and human beings are living on each of them. It is impossible for the inhabitants of different worlds to walk or sit or stand on the same floor because they have different conceptions of what is horizontal and what is vertical. Yet they may well share the use of the same staircase. On the top staircase, illustrated here, 2 people are moving side by side and in the same direction. And yet one of them is obviously going downstairs and the other upstairs. Contact between them is out of the question because they live in 2 different worlds and therefore can have no knowledge of each other's existence." They remind me sometimes of a chemist and an engineer. Although the artist has only used a trick of perspective to influence the mind of the observer, it is a lively, healthy influence indeed for me. Gyroscopes are essentially circular things. A scientific gyro is usually mounted in gimbal rings. So that there is the wheel, here is the inner ring, here is the outer ring. All 3 sets of pivots, the axes pass through the center of mass of the gyro. Now I will tell you what precession is. A torque, by the way, is a twisting force. Instead of a push, which is a force, you push a thing which is pivoted and it twists. So torque is a twisting force. The result of the twisting force is a movement, a rotation, but not in the axis in which you applied the torque. And we call that precession. So I put a torque on the outer ring, it is the inner that precesses. I put a torque on the inner ring, it is the outer that precesses. It will work in either direction. "Oh, you're cheating," I can hear my critics saying. "You're pulling it round as well as doing that." All right, we will satisfy the critics. We will hang a weight from the inner ring so that gravity and not I shall put on the torque. And there you see a precession. Not the sort of movement you really expected, because you are accustomed in higher mathematics to a torque producing an acceleration. Here, a torque produces purely a rotation. And if I put 3 times the mass on, I get 3 times the angular velocity. A different sort of device from our common experience. Now, what I want you to notice this time is, I'll spin it up again because it's getting a little slow. I want you to notice how it accelerates when I put the weight on and how it decelerates, especially how it decelerates. Having been convinced that a torque produces a velocity and not an acceleration, it must have an acceleration or it couldn't increase its velocity at all. And it must have a deceleration when it stops. So let us see if you can determine the rate of deceleration from that sort of angular velocity. When it comes round, I'm going to catch the weight and watch it stop. Hop. Ready again? Hop. There is an acceleration, but it is of a simply enormous value. Let us try increasing the torque by increasing the radius at which things happen. I put this long arm on, and of course it will precess anyway now because of the out of balance mass there, but I can now hang a weight on there and the precession rate increases because the radius is increased. And if I hang it on further along, I get a still bigger precession rate. If I hang it right at the end, you will see it do something else besides merely go round at constant speed. I think I need a fresh spin. Hang on. Incidentally, this shaft has a peg in it. When you buy a toy gyroscope, it has a hole in it. The first thing to do when you bought a toy gyro is to fill the hole in with a peg that sticks out, because you break the string in the hole, and you never do from a peg. Right, I'll reinsert the torque arm. Come on. And when it comes round, I'm going to hang this weight on, and I'm going to let it drop rather fiercely. You see it going up and down as it goes around? That process is called nutation. It is the result of an acceleration as well as a pure precession. Now, the two worlds. The fact that I can press on that and produce a precession of that, either way, has got nothing to do with the fact that I can press on that and produce a precession that way. Because I can hang a weight on this side, and at the same time, I can then attempt to make it go faster than it was going before by pushing on there, just like our volunteer was. And you see, the weight comes up or down. Now we've got something new, because a weight rising means an increase in potential energy. Where did the energy come from? The answer was it came from my finger, because now my finger was moving as it pushed. When I pushed on it and it was stationary, it didn't yield at all, so there was no power input. And even though there's movement of the inner ring, there is no power output, because that moves without being capable of producing any torque. If I resist that motion, then of course it immediately gives way to me. So these are the two worlds, separated for you, as they never are in electromagnetism. We have again been able to make the invisible visible, to dare to make the intangible tangible. Now, scientific gyros are beautiful things like this in gimbal rings that maintain their axis of spin, but the real magic lay in the toy gyroscope, the one you've seen come down the string. Toy gyros are usually supplied with a little Eiffel Tower model, and one of the standard tricks you're supposed to do is to spin the gyro, put it sideways on the tower, thus allowing the force of gravity down on that to be reacted by a normal force from the top of the tower. So you're putting a torque on about a horizontal axis, and that will make the gyro precess about a vertical axis, and everyone is amused. And no one takes it seriously because it is, after all, a toy, isn't it? Fine. Most interesting demonstration. Let us just weigh these two things. First of all, we will weigh the gyroscope. Where's the old bill? That's it. We will weigh the gyro, and we find it to be 310 grams. There are 312 grams. We will weigh the tower and find it to be less than a gram. So over 300 times the weight of the tower. Now, haven't we missed something? Thank you, Bill. What did we miss? We missed the fact that if you ever try to rotate something which is eccentric, not symmetrical, you tend to, yeah, somebody knows, they've tried. You tend to shake your bones to pieces. Now, what is happening when I do that? Apart from me getting terrible shaking, the whole of this is trying to retain its centre of mass fixed. Let us look at the gyro again with that sort of thought in mind. Surely 300 grams compared to 1 gram, you would expect the 300 grams to want to stay in the same place, and you'd expect it to move the tower around itself. But of course it is our common experience that although that happens, the gyro on the tower does not make the tower go round the gyro. 300 times the mass. Whoops. Sorry about that. Can you screw him back in his bearings? Friction on the table. I can hear my critics now. He has friction. We thought we would remove as much of the friction as we could by spinning it on ice. Yeah. Oh, it's come off the tower, Bill. It's all right. We estimate that the coefficient of friction between the tower and the ice is about 0.02, which is just about as small as one could expect to get without going to something exotic. It's a little bit tight on the bearing, Benny. Could you give me the pliers? Did you do it up with your fingers?
Yes.
Oh, it's all right, I can manage. Just a wee bit tight on the pivot. Ah, thank you, Bill. This, of course, is an adjustable gyro. This belongs to an earlier age. Nowadays, they make the flywheels out of aluminium, and what better metal than something that's one of the lightest we know for making a flywheel. So, there it is. This is the modern high standard of living. This is an old-fashioned gyro, about 30, 40, 50 years ago. We have some gyros here today that are 100 years old. So here's a thought. This thing has been with us for 100 years, and we haven't noticed those things which we might have noticed. A tower on ice. Are you convinced? I was. Now this is something that needs following up. And following up means getting a little more scientific and, in particular, making it a bit bigger so that friction has less effect. A gyroscope that can move about a vertical axis, and when I undo this clamp, it has the freedom to drop as well. It is a more sophisticated model of our gyro on the tower. Let us spin this one up and see what happens. that a beauty? You can see a little nutation taking place. I can do the trick I did with the two whirls. I can make it rise up by pushing it a little faster. Notice the precessional speed now is very large because the torque is very large because the gyro is offset a long way. Now, suppose I'd clamped that there and tried to rotate it at that same speed. Watch what happens. Why did it topple? I can't get up to anything like the speed I should do before it wants to take off. It appears to exhibit no centrifugal force. Suppose we were to take this gyro out and put it in a box so that you couldn't see that there was something in the box that was spinning. I'm going to spin it up, put it in the box so that you can't see, and then we'll weigh it, and then we'll put it back on there, and we'll ask a question. They're quite things to handle these when they're moving, aren't they? Right, put him on the balance. And he weighs about 30 ounces, nearly 2 pounds. We put him on the machine. Can you tighten up the nut, Bill? Thank you. Unclamp the middle. There is a black box containing you know not what. And I give it a push the other way. There it goes. I've pushed it round. There's a 2-pound mass with a real angular velocity and no angular momentum. No angular momentum except from the dead weight. It's not rotating. Because if I want to stop it, there's no energy required to stop it, no energy release, because I didn't give it any when I began. Let us go one stage further with this to something bigger, something more scientific we can make measurements of. We go to this machine, which has little buckets around the outside so that I can blow air on them and get it spinning to a quite high speed. Something like 5,000 revs a minute. Don't be alarmed by the noise. When we get this 8-pound wheel up to speed, I shall take a pin out there to allow it to flop like this. And then we shall do experiment number 1, which is to search for centrifugal force. If I bring out the gyro to that position, it is free to topple over. I shall need, in fact, a little weight to hold it down. Of course, in any other position, it's all right. It's only when the offset mass comes out there that it weighs over like that. Now, we'll spin this up, and then I'll take the weight off and ask Mr. Coates to catch the gyro as it falls. Now, if you'll come round there and ready to catch it when I lift the weight, next time round it's coming off. He cheated again, says the man in the gallery. Did he really? Yes, he pushed the aluminium back a bit. All right, he'll pull it forward a bit. More than a bit. Pull it forward a lot. The whole of the tower is now well outside the end of the bench. And if you want me to prove it, I'll show you what happens when the wheel is stationary. Again, it doesn't require much catching, you see. It's gentle as a lamb. Now we'll put the pin back in, and we'll see by how much it overbalances. Well, a lot, obviously. How much? That much? Oh, a lot more than that. That much? More than that. That's it. That much. Over 2 kilograms. Out of balance. And if that looks a ridiculous thing to do, I'm going to spin it up again and then turn it upside down. Yep. Sorry. Got the wrong way around there. Okay. Quite a brute to take upside down. Up to the marks. There we are. When you have seen that, you have seen something you have not seen before. Again, there was the same out of balance 2 kilograms. These gyros are getting larger, and of course, like electrical machines, as they get larger, they get better. Now, what was very interesting about that experiment, I'm about to show you. I'm going to modify this gyro by putting in a second pivot point. And screw that into there, and then the gyro into the end, and now the gyro has 2 alternative pivots. It can either pivot about there or about there. Okay? Which do you think it will elect to do? Bill? The gyro always knows the answer. Do that. It's never going to stay out there, is it? It'd be stupid to expect it to stay out there. Stupid, was it? Well, what about that one? Let's just have a look at what we've just done. The last thing I did was to take a gyro with a pivot there, another pivot there, and then the wheel. And we found that, of course, it elected for that to come down there like that, and the gyro to stick out there, because by doing so there was no change in the axis of spin of the gyro, no precession necessary. Why then did that work? Because there is a bench overhung, here was an aluminium plate, the tower was completely outside the end of the table, a pivot there, the wheel there, and the second pivot there. This thing had the ability, if it wished, to do this and still remain with the gyro horizontal. Why did it not make use of the ability to go like that with the tower there and the gyro still horizontal? We shall see. This is the most remarkable experiment, I think, that I've ever done. I'll balance that, first of all, like a seesaw. So there is a balance point. When I take this out here, of course, then the balance point is upset. It should tip down. We know that given the opportunity, it's going to do this if it can, but now we've balanced it, and we've balanced it about its centre of mass, so that if this gyro transfers its mass centre to the pivot, it should stay balanced. The question is, will it? Let those who say I cannot make a body appear lighter than it is come and pull holes in that one. We shall proceed from larger gyros to still larger gyros. This one, Bill, I think it was. This one weighs getting on for 15, 16 pounds, and we've got some spots on it so you can see its speed, and we're going to anchor it from the roof, showing it like a dog. They get rather big. Now I'm going to put a retort stand under what I believe to be the centre of support. It's a bit difficult when the thing doesn't float, but it's right this way. How is it this way? It's about it. It gives you a general guide as to where the pivot point is. Right, we'll spin her up. When he hands this one to me, it's quite a handful. It has a mind of its own, and you want to turn it round, it says it wants to go back. There's a lot of energy in this wheel. Now, we are now giving it hardly any fetters whatever. It's only tethered to the roof. It's got no gimbal rings. It can go any way it pleases. It must surely want to rotate with its centre of mass over the point, under the point of support. Cranky, buddy. Yep. Cranky, Mum. Right. The Jabberwock isn't the only monster. Over the centre of mass. Oh, there, the centre of support. There it goes. What will it do? "2001, A Space Odyssey." No less. Notice the angle it makes with the horizontal. It's tipped down a bit. In a moment you'll see it rise again. Now it's coming in on a shorter orbit, and the wheel axis is now beginning to tilt upwards. It is going to maintain its centre of mass on a horizontal plane, even though as a conical pendulum it appears to have raised. Now it's actually going out again, and it will perform a number of these orbits from an outermost orbit to an innermost, and it reminds one of an electron, jumping from orbit to orbit, because they're said to spin also. If we have the patience, we'll see it come in again and rise up again, and the gyro wheel is slowing by its own pivot friction, and it is remarkable how low a speed you can get and still have the gyro staying horizontal when it gets close in. It is liable to get settled into a very definite orbit like this, which is the time when I move in and say, "Is he going back?" You think it'll do it itself. It seems to have got rather settled. I'll just disturb it a trifle. Come on. I didn't disturb it enough. Go in. No. What I wanted him to do, no, he won't do it now, I'll have to help him. He's running down, he's running very slowly. But what is surprising is you begin to see the spots now, because he's only running very slowly, and I'm going to slow it still more because of our lack of time. Slow it right down till you can really see those spots, and then say, "Will you still maintain that that shall be your axis of spin?" And he says, "Yes, of course." Look at the rotational speed. It'll soon be down to the stage it's doing 1 revolution of precession per revolution of the rotor. And that is a most incredible machine. Something that you can try on a small scale with a toy gyro like this. Don't ever attempt it with this size, because it is very lethal indeed. Well, would you like to kill that one? Right, we go from bigger to bigger still. This time I call for a volunteer. I shouldn't if I were you. I've got a very specially trained astronaut for this. Come on, Dennis. Here's our chess defeating champion, beating the masters once again. When we stand him on here, I can turn him round with this handle from here. I can spin him round on that platform. So they're going to strap him in very, very tightly. Waist and shoulders. All right. And then we're going to spin up the biggest gyro of the day, which is here. This weighs 18 pounds. The shaft weighs 6 pounds. Would some strong fella like to come and try his strength? Try lifting that up with both hands at one end like that. Who's going to try? Come on. All right, grab hold of the end. Okay? Whoa. Heavier than you thought, isn't it?
Yep.
Try again. Now do it with both hands at one end. You're never going to make it, boy. Right. Now, we're going to give this to Dennis, and we've spun it up to about 2,000 revs a minute. And he's going to show you his feats of strength. Okay?
Right.
Nice and easy. Nice and easy first, Dennis. Take a good hold, that's it.
Hold up. Get it right.
Yeah. Take your hands further back, Dennis.
Happy? I've got it.
You got it. Your hand further back. Pull your hands in.
Well done.
Slow it down.
Okay.
I can make him lower it.
Keep going.
Or raise it. Look at that. Put your arms out, Dennis, if you can. I'm going to shake this young man by the hand. He's got more courage than I ever had at his age. Because he knew... Now it's over, I can tell you, he knew that if he dropped that, it had enough energy that getting a good grip from the ground, it could have hurled itself 200 feet in the air. That was what he held. I'm doing this to warn you against doing demonstrations. We'll do that after this. I think it's more relevant. Can you bring in the... We're going to spin up a small gyro here. Up to about the same speed as we had with that, about 5,000 RPM. And then spin it up with an airline. And then I'm going to drop it deliberately onto a rubber mat. Just to show you how much energy there is in that little thing there. And then you can imagine what that one had. Get it nice and flat against the cardboard. Up a bit. That's it. Mr. Coates is going to try to catch it in a butterfly net. I had to bring butterflies in some way. Right.
You ready, Croc?
Okay. Got it. Here we go. Before we put your lives in danger, we tried it last night with a lot more revs. We got it about half the height of the theatre, coming somewhere over there. There are large amounts of energy at stake here. Now, We'll try this big one again on a stand. On this stand there is a spring. On top of the spring you have a bearing which is free to rotate that way, or a linear bearing to make it go up and down, and we are going to couple this wheel into a pivot. I can never find that though.
That's got it.
And once again spin it up with the drill. Sorry? Tighten up. Now this looks as if it's going to overbalance for sure.
Okay.
Right?
Ready?
If you're careful before the noise starts, as it rises, if I push it round, you should be able to see the spring lift. Okay. Don't go very fast with this. No centrifugal force. I can make it rise, and as I do so, that spring says it weighs less. It looks a monstrous device with all that energy I told you about to have to catch with one hand. It's no problem at all. It has no angular momentum this way. I can lean down also casually and stop it. It is, as I said, as gentle as a lamb. I didn't give it any energy, so why should I expect to receive any from it? Okay, mate. Cool that one down. Are these discoveries new? Well, not entirely. I've had letters from all kinds of people who've done similar experiments before, and for one reason or another have given up for 1, lack of know-how and scientific background, 2, lack of money and workshop facilities, 3, lack of courage, 4, lack of anyone to listen, especially 4. Now today I've got all of you here ready to listen. What a pleasure it is to talk to young people who are ready to listen after you've talked to adults. Quite the most amazing letter I had was from a man who wrote quite unemotionally that he'd performed some of the experiments that I'd done some 10 years ago. And he knew that they worked, but he added, I've not told any of my colleagues or friends because even though I occupy quite a senior post in the scientific civil service, I still have a few years to go to retirement, and I still cherish hopes of further promotion. That is a hell of a thing to say in a scientific world, isn't it? This man dare not tell his colleagues. We talk about blackbirds pecking out the white feathers of their colleagues or killing them if they can't because they didn't conform. This man is afraid of being put away because he wouldn't conform. Now this is not the time or place to go into the mathematics of the gyros. This I can do also. It is not the place to attempt an explanation of the phenomenon, but I cannot send you away hungry, you who have come to listen and to learn. I'm going to go back to an electrical experiment. In this theatre, someone said, Mr. Faraday, what use is all this? And he was my personal hero. He was the man who showed that Ohm's law was only all right for DC. I'm using this coil again. You put DC through it from a battery, and you get 4 amps and 8 volts. That coil has a property all its own, which we call resistance, Ohm's law. And with 8 volts and 4 amps, you get 2 ohms. Now we'll apply some alternating current to the same coil, and we'll get our same 4 amps. You got the wrong scale on, Benny. Can you put the scale right? We're not cheating. You can try this for yourself. This is obviously well known. The voltage is in fact 32. So now we have 4 amps and 32 volts, and we have apparently 8 ohms. We call them ohms, but they're not in Ohm's law. Ohm's law can't have two different values at the same time. The interesting thing is that over 140 years later, we don't say that Ohm's law was wrong. We simply say it is restricted to the use of DC. So, however distasteful it is, we now have to say that object has got something more than a mass. It's got a mass, so long as, and a mass only, so long as we want to push it about in straight lines, weigh it, accelerate it, so on. But if we ever choose to spin it, it has another property, all of its own, which corresponds to the inductance of a coil. This is the updating of Newton's laws of motion. But I'm not saying that Newton's laws of motion are wrong. I'm merely pointing out they are restricted to motion in straight lines and to motion where there is no rate of change of acceleration, just as there was no rate of change of current for Ohm's law. So that is at least some food for you to think about and some indication that I have very strong ideas as to how these things work. So I find no difficulty in saying this thing in a black box had a mass, an angular velocity, and no angular momentum, because we know that in a reactive circuit you have volts, amps, and no watts. What is so difficult at that? And if the abominable no men outside this theatre, this is one of the letters I received, a man called my critics abominable no men. They say no before they've even watched. This 8-pound gyro, we're going to spin it up to a speed that will give about 1 revolution per second of precession. Have we got the bit of wood, my label? Ah. Okay. I'll try and remember the note. That is about 1 revolution per second. I'm going to stick a peg in a hole, and it did not break off the peg because it had no momentum. Now I can tell you that at that speed the same effect can be obtained if I tilt the gyro to 45 degrees, pin it, put it to 45 degrees, and then let it drop. Okay, watch it from the shadow. Didn't break off the peg. I didn't put it in hard enough. 45 degrees. Should have broken. Did this morning. I think you can see there's a much bigger blow effected on it than there was when it was rotating. That's the only loser I've had this afternoon. Not been bad. That also you could try for yourselves on a smaller gyro. No, I have not invented perpetual motion. Of course not. So neither of the scores of people who've written to me saying that they did it before me. Leonardo da Vinci had a picture of a machine like this to dismiss it for all time, that it was impossible. But nobody listened. Leonardo knew all about this. This machine was a perpetual motion machine reinvented throughout centuries. That ball is supposed to roll down that slot, and by increasing its torque and increased radius, it's supposed to bring the next ball in line, and so on, and so on. A perpetual motion machine. Gyroscopes, spinning tops, perpetual motion. Any connection, do you think? Let's try this one. You can see why they cherished hopes, can't you? It takes a long time to settle down, but it would never work. Neither would this one. This is just another reenactment of the same sort of thing. You hope that when that flips over, like that, it'll give enough inertia to bring the next one over and so on. So once given a start, it should just go on. Not a very good invention. But in Switzerland, they really believe in flywheels, gyros. They drive buses with them. They drive buses around uphill and down dale for half a day at a time. There is a Swiss bus, and there is a picture of the gyroscope, or the flywheel, inside the bus. Look at the size of it compared with the man standing alongside. Enough energy to drive a bus for half a day. And unlike the internal combustion engine, when it goes downhill, it effectively pours petrol back into the tank. You see, in Switzerland they have lots of ups and downs, and if they're going to use all the petrol getting up and then have nothing to come back, the flywheel will absorb the energy on the way down. Our little fellow here has done very well, isn't he? You know, it's a perpetual motion machine. I mean, how long do you think we have to wait for that top to stop? Well, I can tell you, you would have to wait 5.5 days and nights. You can see there's something rather odd going on, can't you? Inside there's a whole box of electronics. There's a little mica chip with 6 transistors on it. There's an electromagnet in the center. There's a metal detecting device. And underneath the top there's a little bit of steel. And when it gets near the center, the metal detecting device shouts, "Hey, he's coming," and the electromagnet switches on. And the clever bit is this raised exclamation mark you can see, I think, in the monitor, because the underside of the top is so shaped that when it's pulled in against that exclamation mark, it runs along it, and it gives it, as it were, a lash from a whip. So it's very like the old-fashioned whip and top idea, and of course the top will keep going just as long as there is energy for the electromagnet. And from one very small pocket lamp battery, that will run 5.5 days. That's a nice toy indeed. But if you really want to see our gyro really precesses, then we've made one in which the rim has been subdivided into a lot of little masses on spring wires, so that when I set it in motion, turn it to the camera, you can see this. If I now waggle it side to side, the inner ring that is, you can see the precession taking place not about the point you thought, not about the midpoint here, but about the top and bottom. And if I give the inner ring a spin, you can see this leaning over like a dinner plate. Can you see that? Incidentally, I said that when you had a gyro going, it wanted to maintain its axis of spin. Why isn't that stopping the minute I let go? It wasn't what the other gyros did. There's one for you to think about. I'll answer that next time. Thank you. There is much experimenting to be done. I've only tried offset gyros like that. Relatively simple. What about this one? I counterbalance the mass of the gyro here, so that I've got gyro axis, precession axis, and torque axis. Only the torque and rotor axis meet. And then you can go one stage further and have 3 axes. Sorry, that wasn't the one, that's that one. That one has all 3 axes, skew lines in space. That, torque axis, axis of rotor, all missing one another. What might that do? And we haven't yet started taking energy out of the rotor, which is what an electrical engineer would call radiation. All this and more must be done. Even the mathematics is not beyond A level. The subject is so new, although it's 100 years old, the seas are so uncharted, I've only had time to make replicas of those. Edward de Bono encourages us to do lateral thinking, and his books contain delightful examples. Well, here's a beauty you might like to add to the collection. Gyroscopes do not exhibit a new force. They show a lack of a force where there should have been one. That's why it was so hard to see. A lack of centrifugal. "I see nobody on the road," said Alice. "I only wish I had such eyes," said the king in a fretful tone. To be able to see nobody, and at that distance too. Lewis Carroll must be laughing at us all. If there is a lack of a force, the rest is just pure engineering. We have not yet covered all the situations, especially the radiation one. But above all, never forget, beware the Jabberwock, my son. The jaws that bite, the claws that snatch. There are many heads and many claws, but what an adventure.